Hello everyone, so today we are going to finish up multivariable calculus. So what have we covered so far? Well, we covered geometry, we covered 3D space, we covered vector functions, R of t, maybe we call it. We covered partial derivatives. We have covered multiple integrals and their Jacobians, and we have covered vector calculus. So this is really, again, as I like to think, Calculus 1 is your introduction to looking at smooth functions, right? Looking at smooth functions, I like to think of Calculus 1 as the analysis of smooth functions. You can take real analysis, which covers it again, but again, what you're going to be doing is you're going to be looking at continuous functions, you're going to be looking at how they behave, you're going to be looking at the rates of change, you're going to be looking at their areas. It's very basic stuff. Then you move on to Calculus 2. Calculus 2 I consider to be extremely theoretical. So Calculus 2 is the theory-heavy part of calculus. I personally think it's the hardest part of calculus. So when you need to look at the volumes, you need to look at the integration methods, and then, boy, you need to look at the series and sequences, and those things are really theoretical, and they are so applicable, though. Like, remember when you took a Taylor series and you were able to make a Taylor series into any function you want, then you could integrate it or differentiate it. So we could integrate or differentiate any type of function we like with an infinite series. It's great. But Calculus 3, multivariable calculus, I consider to be the really applicable part. Calculus 1 is nice to have, but it doesn't have many applications. Calculus 3 has so many applications. So much of our life is built around three-dimensional space. And to deal with three-dimensional space or n-dimensional space, you need to deal with multivariable calculus. And keep in mind that everything I've told you throughout this course is with the idea that you can take it to the nth dimension, right? We know how to solve single integrals, and we did a jump from single to double integrals. And that jump was big, but then the jump to triple integrals was smaller. We could do triple integrals. Well, now think about doing an integral with n components, right? Or with n variables. You could do that. We have the techniques. All you need is Fubini's theorem and a good idea of coordinate geometry, although I guess once you get beyond 4 dimensions, you don't need the coordinate geometry. But again, everything we can do is in n dimensions. Vector calc, everything we do in vector calc is n dimensions. In fact, if you go into quantum theory, especially quantum field theory, especially general relativity, you'll be dealing with general relativity, you deal with 4 dimensions. So you need to do integrals off 4 dimensions. In quantum field theory, you need to deal with integrals of 3 dimensions, but then you take Fourier transforms of 4 dimensions, or it's usually multiples of 3. You do 3 dimensions, 6 dimensions, 12 dimensions. But we have the tools to deal with the integrals and the derivatives and the vector calc. Anyways, today we are finishing this off with what I consider the capstone of all of calculus, and that is the divergence theorem. The divergence theorem is very applicable. It's probably the most technical theorem you will have seen so far, although Stokes' theorem is also quite technical, so it might be a little bit less technical than Stokes' theorem. Who knows? Let's get started. That was a big digression, but we can move on. Anyways, we considered Green's theorem for a vector field to be that the closed contour integral of f dot dr is equal to the double integral over the domain that closed contour integral encloses of the divergence of that vector field with respect to a differential area. Okay, now the important part to remember here is that this was for a two-dimensional function and a two-dimensional curve and a two-dimensional domain that sweeps out. Well, let's take that one dimension higher and deal with some oriented surface. This is our surface. Call this surface S, or we call it sigma. Called it sigma right there. Or the volume of that surface is sigma. And then the boundary surface is oriented, so we have a normal unit normal vector, call that n hat, and that goes around the boundary of the surface, and the boundary of the surface we call the boundary of sigma, or you use the partial derivative sign for sigma. Anyways, if I have this fact, and sigma is a solid region with a positive orientation, and then f has continuous partial derivatives, so we're throwing in a vector field there as well, then the integral over the closed surface, the flux integral of f dotted with ds, is equal to the triple integral over sigma of the gradient, the divergence, not the gradient, of f dot multiplied by the differential area. Okay, so with Stokes' theorem allowed us to take a line integral and turn it into a surface integral of some sort of the curl of that vector field. What we are now doing is we're doing a vector field, or we're doing a vector field that is becoming a scalar. So surface integrals in general with Stokes' theorem, these are hard to deal with, and thus these are also hard. But this and this, the line integral, we have multiple theorems for figuring that out. That is easy, relatively. And then this triple integrals, these are pieces of cake. But the surface integrals, we have less fleshed out tools for solving them. So the divergence theorem and Stokes' theorem give us options. They give us opt-outs for surface integrals to turn them into a line integral or a volume integral. Okay, so let's try an example here. Let's evaluate the integral of f ds for the surface bounded by the curves z equals 1 minus x squared, so that's a paraboloid, or parabola, z equals 0, y equals 0, and z equals 2. Okay, so we're going back to that kind of volume definition where we define that as a set of Cartesian points, okay? And the vector function, or the vector field, is xy, then y squared plus e to the xz squared sine of xy. Okay, so what we're going to do first is we're going to find the divergence of f. So we got to find the partial derivative of x, of the x component, so dx of fx is equal to y, dx, or dy of fy is equal, this goes to 0, is equal to 2y. And then dz of fz, well, that's equal to 0 because sine of xy doesn't depend on 0. So if we add all of these up, we get 3y. So the divergence is 3y. And now we do the transform into the divergence theorem. So we're taking the surface integral and turning it into a volume integral over the divergence. So f ds is now equal to the integral over the volume bounded by this series of curves or planes. And then we can integrate with respect to differential element of 3y. Okay, so we pull the 3 out, so that leaves us with y. Now we use the coordinate geometry we spent so much time talking about the last unit to determine our bounds of integration. So I would consider this to be a type 3 region. We've got kind of something that looks a little bit like a log that we're going to be integrating over the volume for. But anyways, you can figure that out yourself. So the integral bounds are from -1 to 1, from 0 to 1 minus x squared, then from 0 to 2 minus c, and of course we integrate y dx dy dz. Now again, you use Fubini's theorem, and then of course all of these will become fairly trivial integrals. That's why we never put like super hard functions in for your divergence, because you'd be tested on getting to this step, or even quite frankly getting to this step. But as long as you get to this step, you're good, and then you can integrate this normally, and you get 184 over 35. But that's besides the point, because the important part is going from the actual surface integral over to the volume integral. Again, something that's really important to cover, a lot of books don't mention this, but the divergence theorem only works if the integral surface is closed. That's why I put so much time putting this circle around the double integral. It looks kind of funky, but it looks, I guess, kind of impressive. So if you forget, always put the circle around the integral, because the divergence theorem and, quite frankly, Stokes' theorem, they do not work if you are using an open surface. That needs to be a closed surface. Okay, so we talked about Maxwell's equation in the last series, or the last series of videos, in context of the curl, the divergence, and then with Stokes' theorem. So it turns out that the Ampere law, Maxwell-Ampere, and then Maxwell-Faraday law have relations to Stokes' theorem, whereas the Gauss laws, there are two of them, one for electricity and one for magnetism, have relations to the divergence theorem. The divergence theorem, another word for it, is actually the Gauss law, and it's because so many laws of physics are derived by using the divergence theorem. And using the divergence theorem actually lets you get rid of a lot of integrals. Okay, anyways, let's talk about Gauss's law for electricity first. We're going to start from the differential form here. So we have the divergence of the E field is equal to rho over epsilon naught. This should make sense. So the any source or sink would be modeled by the charge density over epsilon naught. We're going to go ahead and we're going to integrate both of these sides 3 times with respect to some volume. Okay, so you have the triple integral of the divergence of E dV is equal to 1 over epsilon naught times the integral over V of rho dV. Okay, so now what we can do is for the left-hand side, we can use the divergence theorem. And this gives us that the closed integral of EDS is equal to 1 over epsilon naught times the integral of rho dV, but the integral of rho dV is actually defined to be the charge enclosed by this surface, so the charge enclosed in the volume. Okay, so this is also equal, this is equal to the electric flux as well, so that's equal to the electric flux, which we call capital phi sub E. And essentially you can see what happens here. If you want to find, you usually use the form, that the surface integral of EDS is equal to Q over epsilon naught. And you can use this to find, usually E. You want to find the E field. So what you would do is, given some charge distribution, might look like that or something, but you know how much charge is inside of it. You choose a Gaussian, what you call a Gaussian surface, and you try to make the Gaussian surface super easy so that the electric field across the Gaussian surface is constant. Okay, so usually you use a sphere, you could use a cube, you could use a cylinder to surround your charge distribution. But the reason that you do this is that the surface integral just becomes, the ds would become like, for a sphere, it becomes 4 pi r squared, and then times the double integral over E, but that's not, none of this is constant. So you pull it all out, and then the double integral goes away, so you get like 4 pi r squared E equals Q over epsilon naught. And then you can continue on with this derivation. I may have missed a sign here, but no, I don't think so. I think this defines Coulomb's law, actually. Yes, because you will have E equals Q over 4 pi epsilon naught r squared, or Q over K r squared, which is, of course, the electric field defined by Coulomb's law, which says the force is equal to KQQ, or this K goes upstairs, actually, KQQ over r squared. Okay, there's also a Gauss's law for magnetism, but it isn't really worth going over because it's very similar. The Gauss law for magnetism essentially says that magnetic monopoles cannot exist. So the divergence of the B field needs to be equal to 0, so anything coming out of a source needs to go back into a sink. Okay, and this translates simply to that the double integral over dv of b dot ds is equal to 0. I would consider this to be fairly trivial, but both of these laws are very important in the field of electricity and magnetism. Okay, so that is all we have for multivariable calculus. I hope you enjoyed this series. What to do next is really a big question. I'm thinking possibly complex analysis. We could go into linear algebra, but I would be more interested in going into complex analysis or perhaps differential equations. But it really goes to show that after you've finished with advanced calculus, the world is your oyster. You really don't have any restrictions to the math you can now take. It's no longer a line, it's more of a tree. Anyways, that's my spiel. If you made it through the series, wonderful job. Thanks for making it through all of my dronings. on about these interesting math concepts, or maybe not so interesting math concepts. But yeah, thank you, and we will see you soon. Bye.